Uno, dos. ¿Se escucha? 1, 2, 3, 4, 5, 6.
Ahorita nomás unos 2 minutitos y listo.
Sí, ya llegaron.
¿Ya llegaron?
Sí.
A ver, captura de... De hecho, mira, ya me toma en automático esto. Voy a checar una transmisión.
Well, good morning, everyone. Welcome. We are starting this third conference day, and we have the keynote elders. And let me introduce to our keynote speaker. He is Professor Efrén Mezura-Montes. He's a full-time researcher at the Artificial Intelligence Research Institute at the University of Veracruz in Mexico. His research interests are designing, analyzing, and applying bio-inspired algorithms to solve complex optimization problems. Professor Mezura is a member of the IEEE Computational Intelligence Society Evolutionary Computation, and also he's member of the IEEE Systems, Man and Cybernetics Society Soft Computing Technical Committee. Also, he is a regular member of the Mexican Academy of Sciences, and he is Vice President of the Computer Science Mexican Society. Then, welcome, Professor. Thank you very much for being here. Will you please start your keynote?
Okay, thank you. Thank you for the nice introduction. And thank you to the Organizing Committee for this invitation. This talk is about bio-inspired algorithms. This is a conference on pattern recognition, so maybe the first question is why evolutionary algorithms here. So I hope at the end of the talk you have some hints about the importance of this type of search algorithms in pattern recognition and also general machine learning. Okay. Okay. The agenda is this one. I will briefly talk about my institution. After that, I will talk about a little bit of history of evolutionary and swarm intelligence algorithms. It is important to know history about the area that you are doing some research. After that, I will talk about more recent algorithms, important algorithms that are very popular nowadays. I will talk about swarm intelligence, which is different with respect to evolutionary algorithms. Even in the specialized literature, maybe it's a little bit confusing about that, but they are different. And then I will talk about the little mess that we have right now, with this explosion of different bio-inspired algorithms and also inspired to other metaphors, and the problem that we have because of that. I will try to explain what's happening. It's my personal point of view, so if you have any critics, welcome. And finally, if you are interested on using this type of algorithms, I will give you a brief user guide, how to select the most suitable algorithm for your work on body recognition. Okay? So let's start the talk. We are in the Artificial Intelligence Research Institute in Veracruz. We are in the middle part of the state, close to the mountains, but also close to the sea. Jalapa is the capital city of Veracruz, and there is the South Campus of the University of Veracruz in Jalapa, and there is the Artificial Intelligence Research Institute. University of Veracruz and also Lithuania in 1994 proposed the first graduate studies in artificial intelligence, 1994. So those colleagues were very smart to start talking about artificial intelligence those years ago. So University of Veracruz is one of the pioneers in artificial intelligence. We also have a PhD in artificial intelligence. The 30th anniversary next year. Okay, we are grouped in academic bodies. We have 3 of them, also a 4th one is a recent proposal. I'm collaborating in the first one, Artificial Intelligence Research and Application, which is very close to the topic we talk today. There are colleagues working on robotics and also on sensors, information sensors. And there is also a group of physicists that use artificial intelligence to solve some problems in physics. So this gives you a general idea about the type of research that we are carrying out in Jalapa. The research group that we have is called CONACyT, which joins different areas, in this case computer vision, neural networks, evolutionary computation, and their applications. This is our group. At the institute are my colleagues working in that group, Marcela Quiroz, Randy Barrientos, Hector Gabriel Acosta, and myself. And we have also a very important group of students working hard, doing very good research on these topics. Okay, let's talk about bio-inspired computing. This idea comes from a metaphor found in nature, which is adapting to survive. It is important for species to adapt to the environment, to survive, and to let offspring to generate other offspring and then guarantee that survival of the species. But as you can see, for example, here there are 2 types of bears, polar bear and a grizzly bear. All of them are bears, but they are different. Why are those bears different? This is because of the influence of the environment that they live. So if we accept this evolution theory, we can say that this type of species can adapt to the features of the environment. So this idea is taken as an inspiration to generate search algorithms. It is a very interesting way that in the middle of the 60s, in the middle of the 60s, the same idea was proposed in 3 different places with 3 different motivations. The first one was in Germany, with Ingo Reichenberg. They tried to solve some problems in the engineering field. And they have different mathematical programming techniques at that time, but the results were not so good. So in his group, they proposed to use evolution as a way to generate a search algorithm that improves the quality of the design that they try to optimize. And they called their approach evolution strategies. In the same years, University of California in Los Angeles, Lawrence Vogel, they were trying to solve prediction problems. And at that time, they used finite state machines, automats. However, these machines were huge. So they tried to simplify that model in an automatic way. So they proposed to evolve these machines to make them easier to understand. Then, based on this idea, they proposed evolutionary programming. Finally, and this is maybe the most popular algorithm, John Holland, University of Michigan, they have some problems with classification, and they use rules to classify data in the biological area. But the number of rules was significant, so they tried to simplify the number of rules in an automatic way. So they proposed what he called the reproductive plans. But later, the proposal was called genetic algorithm. So as you can see, with very different motivations, the same idea is proposed: evolution in a computer. These algorithms use a metaphor called neo-Darwinism. Neo-Darwinism joins the idea of Mendel, Weizmann, and you know this guy. You know this guy? Charles Darwin. Maybe he's the most famous. But neo-Darwinism joins the idea of Darwin, Weizmann, and Mendel. Weizmann, in research, proposed that there are some cells in living organisms that are capable to inherit characteristics from parent to offspring. And Mendel experimented and defined those inheriting rules. So with all this idea, we have this term, and this is the base of evolutionary algorithms. So what we have is a set of search algorithms which emulate the theory of evolution in neo-Darwinism, the survival of the fittest, and they are very popular to solve optimization problems. The connection with machine learning or data mining, pattern recognition, is that there are several search problems when you work with data and when you try to find patterns. The way an evolutionary algorithm works is very simple. You have a population of individuals, which are solutions to the problem that they're trying to solve. And then you extract, you separate those which are the better based on a fitness function. You separate them and you call them parents. These parents are the best one from the population, and they will be able to reproduce, to generate offspring. Then you can expect that these offspring are better than the parents. That's the idea. However, as you can see, the size of the population has increased because you have the original population and now the offspring. The final process of an evolutionary algorithm is called environmental selection or replacement, which is just to cut the size of the population to get a similar number as the one I had at the beginning, and then iterate several times. At the end, in this population, I will have a very good solution for the problem I'm trying to solve. That's the idea. Okay? After the 60s, in late 80s, John Cosa, University of Michigan, he was a PhD student from Holland. He proposed the fourth paradigm of evolutionary algorithm, which is called genetic programming. Genetic programming is very similar to a genetic algorithm in the way that they work. However, there is an important difference. Genetic programming works with a very particular representation, trees. So now you can represent and work with this type of structures to optimize. With symbols, not necessarily with numbers. That's with symbols. And finally, in the mid-90s, the last evolutionary algorithm was proposed. It was by Raymond Storr and Kenneth Price. And they proposed differential evolution. Differential evolution is a very simple algorithm which has close connection with mathematical programming, but it is very easy to implement, and it is very effective to solve several types of optimization problems. And the idea is very simple. Vector differences. They observe that difference of vectors define a search direction. So based on these different search directions, just based on two solutions, you can have different possibilities to generate new solutions. And based on this very simple idea, they generate a very powerful algorithm. If you type differential evolution in Google, you will note the high amount of research that is about this algorithm. Okay, you generate a lot of solutions with just vector differences. Very simple. Okay. After these 5 well-known evolutionary algorithms were proposed, swarm intelligence appeared in the mid-90s. The first proposal was by James Kennedy and Russell Everhart. They proposed the particle swarm optimization algorithm, which is based on the choreographies that some bird flocks follow in the sky to find food. And also, in the same years, Marco Dorigo proposed the ant colony optimization algorithm. Okay? But these two are not evolutionary algorithms because the metaphor is very different in this case. Swarm intelligence doesn't use evolution as a metaphor. Swarm intelligence regulates social behaviors of very simple organisms, where the communication is the key to generate an interesting behavior, collaboration. And after these two algorithms were proposed, what happened? And now we start with a little mess. Okay? Several bio-inspired algorithms were proposed in those years. For example, the bacterial foraging optimization algorithm by Pacino in 2002, based on the egg bacteria that we always have. Artificial bee colony by Caraboga and Bastur in 2003, based on the behavior of bees when they look for food around the nest. The cuckoo search algorithm. Do you know that the cuckoo bird algorithm is very curious behavior in nature? Another approach proposed. So now we have several algorithms of this time, but not only biology based, but also based on physics, based on human behavior, and there we have the evolutionary algorithms. So the area grows in number of algorithms. Okay? You have plenty of options to choose the algorithm to solve your search problem in machine learning. And okay, that can be good, but not all the time. Okay? So there are some critical voices about this type of proposal, new proposals. Okay? And this paper is very famous, was published in the International Section in Operational Research in 2015. And it's called Metaheuristic, the Metaphor Exposed. But positive things, not all is bad. The author found that there are some very well established metaheuristics, search algorithms, like simulated annealing, evolutionary algorithms, and color compensation, and others. And he considered that new ideas are welcome. However, there are negatives on these proposals. For example, if you go through these type of papers and you see and you try to understand the metaphor of the algorithm, for example, the harmony search algorithm based on music, or the bath algorithm, or the water drop algorithm, or the firefly algorithm, or the firework algorithm. The terminology is very confusing, okay? And also, if you go a little bit further in the algorithm design, you find similarities regarding the type of search operators that are proposed. And if you are a little bit critic, you can see that several of them are based, for example, in those proposed years ago by the German guys in the evolution studies. And several of them use the vector differences as the base of the operator, maybe defined as a bee that goes to a flower. or a glowworm shining in darkness. Okay? But at the end, the operators are very similar. So nobody is questioned. And it is also hard to explain because you need to know about several metaphors to understand a search algorithm. So if you are not from the area, it is very difficult to understand all of that. At the end, you need a search algorithm. That's the goal. So it gets you confused, and it is not good. Okay? More negatives. Poor clarity about the superiority of new algorithms. The experimental designs are questioned. The authors claim that, okay, my algorithm is very good. Tons of experiments and results. But if you go further and analyze those results, they don't compare against state of the art necessarily. But they claim that the algorithm is good. So it's really good. The proposal is really good. You need to beat the good ones. Okay, sorry. So the metaphor is more important than the search mechanism. And we are trying to find a metaphor, a nice metaphor. Okay? And as I mentioned before, maybe we have a very well-known operator, and I just rename it, trying to adapt it to the metaphor that I'm trying to propose as a new search algorithm. So I'm more interested on improving result rather than understanding it. Okay, so let's reflect. In 2019, this paper was published. Important colleagues of the area are co-authors. This paper was published in a very good journal here, which, as you can see, coupled swarm and evolutionary algorithms. And they found that, okay, it's a timeline. As you can see, the 60s, you can see the three algorithms that I already mentioned. Evolutionary programming, evolution strategies, genetic algorithm. But what happened after that? Okay, genetic programming, differential evolution, particle optimization, and colony. But if you go to, for example, 2014, you can start seeing a lot of algorithms. You can see the names here. And also, if you can see the behavior of the publications on evolutionary algorithms, which is this plot here, and this is the search on swarm intelligence, you then see that swarm intelligence is more attractive nowadays. But maybe not for the important reasons, as I mentioned before. Trying to generate the new algorithm, the most elusive algorithm, claiming that it is the best one. I don't know if this is the good way to get in a mature area. Okay, I mentioned that. Again, timeline. As you can see, for example, early in this millennium, we have a lot of theoretical and also empirical analysis on evolutionary algorithms. I mean, the first bar is easy, evolutionary algorithm. The second one is swarm intelligence. As you can see, swarm intelligence has a little research early in this millennium. However, as you go here, this is evolutionary computing and this is swarm intelligence. Okay? I am not against swarm intelligence. I use swarm intelligence. I like swarm intelligence. Okay? This is a graph where all the areas that biospheric computation is covering, the authors present these general ideas, if we have a zoom here, we can see that there are a lot of applications, for example, pattern recognition. There are also parameter tuning, parameter adaptation. These algorithms require to define parameters. And it's important to get good techniques to do that. I mean, several methods that we use have parameters. So we need to be very careful when we define them to get solid evidence. So this important work regarding these topics. And also an idea which is very popular nowadays, which is called memetic algorithms, which is the combination of a global search algorithm like evolutionary algorithm, usual intelligence, and also local search to refine good solutions. And it is very useful when you try to find good solution in a shorter time. So the author of the paper, and I agree with that, we need to get a mature area. So we need more theory. Okay, we have the Northridge launch theorems, that's very good, but we also need works on, for example, the fitness landscape, the popular exploration exploitation balancing. For example, we have interesting concepts like novelty search. We discard the fitness function. If you know a little bit about evolutionary algorithms, and I say you, okay, in your algorithms you will not use a fitness function. You say, what? Okay, you can not use a fitness function. We will use novelty to guide the search. And we avoid evaluation of solution because in some problems it's very costly. For example, in neural evolution, if you try to evolve the architecture of a deep neural network, and if the neural network is designed for classification, its process is costly. Maybe it can be attractive if you can avoid it. Okay? And getting a good deep neural network for your problem. Okay, we need to solve more dynamic and robust optimization. We are very interested in the best solution, but in real world, maybe the best solution is not the important one. We need robust solution. A robust solution is the one that is tolerant to changes in the problem. It is a good solution, but if you change some parts of the problem, it remains a good solution. So maybe robustness is better than optimality. And we are also working in the group, we are working in bi-level optimization. You can have nested optimization of search algorithms. And this is very important because you can model problems in a better way. There are a lot of work, for example, when you deal with different objectives, multi-objectives, 2 or 3 fitness functions at the same time, or very many objectives, 4 or more. Multimodal optimization, when you can offer the user different solutions, but with the same quality. So the expert can choose from different solutions, and this is very attractive, because all of them are good, and you can select the best one for you. Multimodal optimization. Surrogate assist by inspired algorithms. This is important because, as I mentioned before, some problems are costly to evaluate. So you can generate a surrogate model, which is, you can use statistical models, but you can also use machine learning to generate a model that tries to approximate the costly model, and then you evaluate some solution in this cheap model. Okay? The idea is very simple, the implementation is very hard, but it is a good option. Distributed by inspired algorithms is a very interesting area because you have populations in different, there are separate. You can modulate migration, for example, involving different populations in different computers, and then let them migrate some solution from one population to another population, and let them generate offering and stuff like that. And finally, ensemble of this type of bio-inspired algorithms. This is a very nice paper, 2019, where you can see a survey of evolutionary machine learning. And these are all the topics, as you can see, the evolutionary machine learning, application, task, image analysis, scheduling, deep learning, and other topics. Okay? And then his colleagues propose a very good taxonomy of different specific topics that you can see. For example, this classification, regression, clustering, image processing, for example, evolutionary clustering, feature reduction, regression, deep learning, neural network based evolutionary deep learning, genetic programming for deep learning. There's some feature selection, feature consumption, etc., etc., etc. So you can improve your machine learning work if you use evolutionary algorithms. That's the goal of my talk. Okay? Because if you use machine learning, you need to define several parameters, several aspects in your modeling approach. And maybe an evolutionary algorithm, swarm intelligence algorithm, can help you to do that. Okay? And this is the proof. This is the web page of one of the two most important international conference on evolutionary computation. And these are the special sessions. And as you can see, for example, this one, data-driven evolutionary optimization of computational expressive problems. Using machine learning to help the evolutionary algorithm to perform a better search. For example, using previous experiences that helps the evolutionary algorithm to learn from these experiences and then perform a faster search. So machine learning can also help evolutionary computing. Other options, evolutionary deep learning and applications. It's very common. Neural evolution, neural architecture search. You don't need to adopt a deep neural network because it's the one that you found. You can generate your own one. You can evolve your own one based on the objectives, the fitness function that you need. And you can optimize more than one fitness function. Evolutionary transfer learning, transfer optimization. Transfer learning is also, you can also use transfer learning with evolutionary algorithms. Evolutionary computation for automatic design of machine learning and search. Auto machine learning, okay. You can do that, these pipelines with evolutionary algorithms. It's very, very common nowadays. Evolutionary multi-objective machine learning, using multi-objective optimization to optimize machine learning models. Evolutionary computation for feature selection, feature extraction, dimensionality reduction. Very common in very particular areas in which have data sets with a lot of features. You need to reduce it. Maybe not only the features, maybe the instances as well. To optimize the process because training is costly. Why not optimize? This is the other important conference in the area, GECO, Genetic and Evolutionary Computation. I didn't mention the name of the previous one. This is the IEEE Congress on Evolutionary Computation. It's next week, Chicago. This is GECO, Genetic and Evolutionary Computation Conference, organized by ACM. It's in Porto in 3 weeks. And GECO is organized in tracks. We have the evolutionary machine learning track. Tracks are very important in GECO. It is very hard to get new tracks in GECO. We have now one in evolutionary machine learning. GECO has a acceptance rate of 22%. It's very hard to publish in GECO. And they are interested in evolutionary machine learning. Another track, neuroevolution, 2 years. Neuroevolution as a track. These are workshops in Gecko. Workshop on enhancing generative machine learning with evolutionary computation. Generative AI, evolutionary rule-based machine learning, evolutionary reinforcement learning workshop. Again, all the three types of learning are covered with evolutionary algorithms. Okay, we have a lot of challenge in the area. Many algorithms, it's not necessarily good. We need good algorithms. We need to unify terms. We need to focus on efficiency. This is very important, and that's the reason I am here. New computing paradigms. There was a very nice talk yesterday on quantum computing, so it's a very interesting area. If you want to know how many algorithms of these types are available, we have this paper. You can go and check. At that time, there were 2,090 inputs. If your advisor says, okay, please choose one bio-inspired algorithm for your work, you have 292 options. Which one is the best one? Oh my God. And you need to justify your decision. Not the nice one, not the easiest one, the best one for your work. Okay, a lot of them. So, to start our conclusions, what we observe right now is like a search in a population-based algorithm. We have exploration, this is the search space, we have solution about all the search space. We don't try to find a good solution, but we have solution in all the search space, very different solutions. We look for this exploitation phase. We try to concentrate solution, try to find the robust, the optimal solution, the best one solution. Okay? Exploration and then exploitation. That's how this type of algorithms work. Okay. This is what is happening now. We are in an exploration phase. Several algorithms, several of them. What we are expecting? The exploitation phase, where only the best algorithms will prevail. And then we have a mature area. And if you need an algorithm of this type, you maybe need to choose, but not among 292 algorithms. Okay? Okay, I mentioned that, the metaphor of exploitation. Finally, the use of guide. And it is also based on a paper published in 2022 in the same journal. Step 1, select your algorithm based on information. Specialized literature, always. It gives you the best hint. And after that, prefers consolidated algorithms. Don't do what Alice did in that story when she asked the cat what path she needed to follow, if you remember that story. Okay? Don't do that mistake. Okay? Step 2, select your test beds wisely. If you are working with real-world problems, real-world data sets, there is a particular way to do that. If you are using data sets already processed, very well known, balanced, etc., okay, that's another way. But you need to be very clear on the path that you are following. Always use recent algorithms for comparison, it's very important. And select performance measures that are very useful to prove that your approach is competitive in the way that you need to prove that. It's very common to choose wrongly performance measures. Okay? Always validate your result if you are using this type of algorithm. They are stochastic. I will talk about that tomorrow, tutorial. They are stochastic. You cannot measure the performance based on a single run. We need to carry on statistical tests to provide solid evidence. It is not good to say, okay, I run my genetic algorithms one time and this is my solution and it is very good. I'm very happy. It's not correct. Okay? And please show the results in a very clear way. Step 4, if your approach have different elements, you need an ablation analysis, and you need to analyze the effect of each one of the elements of your algorithm separately to determine the importance of those mechanisms in your algorithm. Otherwise, you don't know nothing about your algorithm. You only know that it works, but you don't know how. You don't know, you have any idea about the type of mechanism that is important to do a good search. And it is very common when you use a new metaphor. You have no idea about the new mechanisms. And also, take care of the parameter analysis. If you are using tuning, you are calibrating your algorithm, please provide good evidence on that. Otherwise, your evidence can be considered as weak. Or maybe use as adaptation or self-adaptation of parameters. But you need to be very careful on that. And it's important for all the fetch to remark the novelty of your proposal. And remember, a new metaphor is not necessarily novel. So please, if you are going to choose the most recent values-paired algorithm, think twice. Okay? And that's it. Thank you very much.
Thank you, Professor, for the interesting talk. Then we have time for questions. Do you have any questions? I have one. From your experience, have you applied some of the main evolutionary algorithms to a real problem?
Thank you. Yes, and actually we'll talk more about that tomorrow. Trying to advertise my tutorial. Yes, we are working particularly with medical applications. We are working with datasets particular for cancer, and we are working with images and also with traditional data. In all cases, when you use the traditional machine learning approach without the evolutionary algorithm, you get some results, but if you use them wisely coupled with the evolutionary algorithms, you get better results, particularly in medicine. And medical imaging is the most relevant part in our research, application research. And more recently, we are working also on the electrical engineering transformer design. And we are also doing a lot of neural evolution because we have applications in different domains that need these neural networks, but it is not easy to get the architecture manually. So we let the evolutionary algorithm or the swarm intelligence algorithm to avoid this type of algorithms. During the pandemic, we worked with X-ray images, COVID images, and stuff like that. We are very close to the medical applications.
Thank you. Another question. We have one question.
Thank you. Thank you, Efrén, for the presentation. Very interesting. When I did my PhD like 20 years ago, I used to work on Spark computing. I work on artificial immune systems, and I attended GECO, CDC, And at that time, there was like a division between the people of soft computing and the people of traditional AI. And people of neural networks at that time were like in the middle. Because in CEC there was like a conference on neural networks and then evolutionary computation and fuzzy. But it seems like the people of machine learning moved to more to the traditional AI and their own conferences. I want to know how is the situation nowadays on the evolutionary computation and machine learning, because it seems like still that there is that division.
Thank you for the question. Yeah, division, always present. There's division within AI. Traditional AI is symbolic. So AI nowadays is symbolic. Neural networks, numbers. It's very hard to understand this type of very efficient algorithms. Okay, so within AI there's a division. Now, as you can see, at least the evolutionary computing area is now very open to collaborate with people from machine learning. So, the number of special sessions, the tracks in Gecko, is a signal of this close connection. And I hope this invitation today here is another signal in Mexico to get these communities closer. Because, for example, just as an example, if you, for example, you use decision trees, and you use the traditional algorithm C4.5 algorithm to generate your tree, this algorithm is a search algorithm. But it is a trajectory search algorithm. Have you ever questioned that this tree, that this very well-known approach in machine learning generate the best tree for you? Why don't you try an evolutionary algorithm? And if your approach, if your tree generated with the traditional method is better, there's no problem at all. But what if the tree generated with the evolutionary algorithm is better? Tomorrow I will talk about a recent survey that we published in a journal, just about meta-heuristics for decision trees. We have more than 200 references just for decision trees. Now that we are also working on neural evolution, neural architecture research, we see tons of work right now. So I think there are good news about that. And I see, as my point of view, that maybe 5-10 years, this relation will be even closer. Okay? Thank you.
Have another question.
Thank you. My question is just about, you talk about many algorithms available, but also recommended to use the more consolidated ones. How can one recognize a consolidated algorithm, evolutionary algorithm from all the ones available, right? Which secret criteria, besides perhaps number of citations?
Thank you. That's a very good question. Thank you. It is not an easy task, but maybe you need to check, for example, the proceedings of these two conferences. For example, Gecko and CICESE, because they are very solid in the type of paper that they accept. And also, the recent papers on the most important journals in the area. So, evolutionary computation, IEEE transactions with computation, evolutionary computation from MIT Press, and there are others. And you will see that most of the work is on the same type of algorithms. You won't see in those type, and you can find one paper maybe, but most of the work is on those consolidated approaches. So maybe it is a possible path. Otherwise, we can establish some contact, and I can suggest you, based on the type of problem that you're trying to solve, which type of algorithm you need to use. Because I am aware that it's not an easy task right now. Let's wait for the exploitation phase, and you will have just less algorithms to select from. Thank you.
Well, we have time for a final question, if there is one.
Thank you, Efrén, for the talk. My question is about exploitation. You commented that the best algorithms will remain. Will you share with us your view what are the best one at this moment,
Of course.
from your experience point of view?
Yeah, thank you for the question. Okay, nowadays, for example, we are working with single objective optimization. Differential evolution is a very good choice. Particle sort optimization is a good choice. Mainly for numerical optimization. If you move to combinatorial optimization and colony would be a very good choice. If you move to multi-objective optimization, NSGA2, which is based on a genetic algorithm, is the best of the best. At least for this type of problems. You move to multimodal or many objective, maybe you need to check the literature to see the tendencies, particular for the problem that you're trying to solve. But these algorithms that I already mentioned, maybe are, as I said, it's a very good starting point to solve the problem that we are trying to optimize in pattern recognition machine learning.
Thank you. And to finish this keynote session, we have the organization committee. We thank you, Professor, for your participation. And we have a certificate of participation for your interest. Thank you very much. In addition, we have a couple of presents for you. Thank you again. When we finish this keynote session, we start the next session. Thank you very much to everyone.